Number 10. Chemical rockets. September 5, 1977. The Voyager 1 spacecraft, launched from Cape Canaveral, was a science mission designed only to study Jupiter and Saturn that day. No one expected it to do more than that. But half a century later, Voyager 1 would become the farthest of everything humanity has ever sent into space, having crossed the boundaries of the solar system and still flying. It travels at a speed of approximately 61,000 kilometers per hour. This figure sounds impossible until you do this calculation. Our nearest star system, Alpha Centauri, is 4.24 light-years away. If Voyager 1 continues at the speed, it will take 73,000 years to reach there. This is not a rounding error. This is a wall. Chemical rockets generate thrust by burning propellant and exhausting the exhaust at high speed. The Saturn V, the most powerful rocket humanity has successfully flown to date, achieved a specific impulse of about 450 seconds for every kilogram of fuel. This was unique for carrying humans to the moon. If the goal is to reach another star, it is a deep and almost insulting inadequacy. Tsiolkovsky's rocket equation reveals the situation in all its realism. The faster you want to go, the more fuel you need. The more fuel you carry, the heavier you are. You want even more fuel, and this cycle is never resolved. Even the cleverest trick called gravity assist, stealing momentum from the orbits of planets, only takes you a few small steps forward. NASA's Parker Solar Probe reached speeds close to 690,000 kilometers per hour while traveling around the Sun. It was the fastest vehicle in human history, but it was still below 0.1% of the speed of light. The energy stored in molecular bonds, no matter how clever the engineering used, cannot produce the exhaust velocities needed to cross interstellar distances in a time frame a living civilization cares about. We knew this even before the first rocket flew. Chemical rockets will carry our legacy outward. They are the results of our attempts, but they will never carry us to another star. And with their silent mathematical certainty, they remind us nothing we have built so far is enough. However, this inadequacy, compared to what we will talk about at number 1 on our list, remains like just a tiny spark. Because what awaits us there is about distance itself. And that truth emits a much brighter flame than the limits of chemical rockets.
Number 9. Nuclear thermal propulsion. It was the late 1950s, in the middle of the Nevada desert in an area known as Jackass Flats, about which the public knew almost nothing. NASA and U.S. Atomic Energy Commission engineers were quietly working for something unprecedented. They named the program NERVA, Nuclear Engine for Rocket Vehicle Application. Between 1955 and 1973, they designed, built, and tested more than 25 working nuclear rocket engines, and none of them could even lift themselves off the ground. Nuclear thermal propulsion is conceptually simple. Instead of using chemical propellants, a nuclear fission reactor heats liquid hydrogen to extreme temperatures, and the superheated hydrogen is expelled through a nozzle to obtain thrust. The advantage is immediate and clear. Nuclear thermal engines can generate a specific impulse of 800 to 1,000 seconds, which is almost twice that of the best chemical rockets humanity has flown. More thrust, more efficiency, more speed. From a reactor that does not require oxygen, without the need for combustion, and without producing a flame, in the NERVA XE engine test conducted at Jackass Flats in 1969, engineers performed a full-power demonstration proving it worked perfectly as physics predicted. NASA even created draft mission profiles for a nuclear-powered Mars expedition. The technology was real, proven, and ready for development. Then in 1972 and 1973, as the Apollo program ended and congressional budgets collapsed, NERVA was canceled. Not because it experienced failure, because the money was cut. A nuclear thermal rocket pushing a spacecraft at 30 to 40 kilometers per second would still need tens of thousands of years to reach Alpha Centauri. Faster than chemical, but still laughably inadequate on a cosmic scale. In 2023, NASA and DARPA awarded a contract to Lockheed Martin and BWX Technologies under a program called DRACO to demonstrate nuclear thermal propulsion in orbit. The technology is being reborn, but the main question remains unanswered. It didn't take long to understand if nuclear rockets worked. We knew that already. Do we have the patience to build what comes after that? This is a more important question.
Number 8. Nuclear pulse propulsion, 1958. A physicist and an engineer were sitting at a wooden table at General Atomics in California. Freeman Dyson and Ted Taylor. In front of them there was only paper and a calculator. What they were doing was creating the most unrealistic spacecraft imagined to that day, and on paper, it worked almost flawlessly. The propulsion system was both simple and terrifying to the point it couldn't be ignored. Launch a nuclear bomb behind the ship. Absorb the explosion through a giant steel pusher plate connected to shock absorbers. Repeat. Hundreds of times. Thousands of times. This project's name was Orion. This concept had a history going back to 1947 by Stanislav Ulam. It wasn't the idea that made the project perfect, but the engineering detail. The team calculated that nuclear pulse propulsion could achieve a specific impulse between 2,000 and 12,000 seconds, 5 to 30 times more efficient than chemical rockets, moreover, along with massive thrust. Since then, no proposed technology has offered both features at the same time. The Orion team calculated they could reach Mars in a few weeks and the moons of Saturn in less than a year. With a sufficiently large interstellar version, it was possible to reach 3 to 10% of the speed of light. Orion was halted in 1964, immediately after the year the Partial Nuclear Test Ban Treaty, which prohibited nuclear detonations in space, was signed. The engineering was successful, but politics made it illegal. 15 years later, in 1978, the British Interplanetary Society published Project Daedalus, further specializing the same concept over 5 years, a 2-stage fusion pulse vehicle detonating 250 deuterium-helium-3 pellets every second. Total weight? 54,000 tons. 50,000 tons of that is fuel. The target speed was 12% of the speed of light. Destination? Barnard Star, 5.9 light-years away. Estimated arrival time? 50 years. Fuel would be extracted from Jupiter's atmosphere. 2 independent engineering studies conducted 15 years and an ocean apart got the same answer. Carefully directed nuclear detonations became the most reliable method humanity ever put on paper to reach another star. Both died before they could leave the drawing board. And the stars are still waiting.
Number 7. Bussard Ramjet, 1959. A breakfast table in Los Alamos. As Robert Bussard looked at the rolled tortilla placed in front of him, a thought so clear came to his mind that he spent the next year turning that thought into a scientific paper. If the thing that limits every rocket is carrying fuel, he asked, why carry any fuel at all? Interstellar space is not empty. It is filled with atoms of hydrogen, the most abundant element in the universe. But what if this hydrogen were collected while you were flying, entered a fusion reactor, and the universe itself became your fuel tank? Bussard presented this perfect idea in his 1960 article titled Galactic Matter and Interstellar Flight, published in the journal Astronautica Octa. The design would be a massive electromagnetic field, which could be hundreds or even thousands of kilometers in diameter, ionizing and collecting hydrogen atoms from the interstellar medium and directing them to a fusion reactor. Since the vehicle would carry no fuel, it would also escape the limitations of the rocket equation. Theoretically, it could accelerate indefinitely and approach the speed of light within decades. A round trip to the nearest galaxy of the universe would be possible within a single human lifetime. This idea became famous. It entered Carl Sagan's texts. Paul Anderson built a novel on an unstoppable version of it. In Star Trek, the names of the parts glowing red at the front of every ship are explicitly Bussard collectors. This is a silent admission of how seriously the physics community once took his idea. Then the problems started coming. The interstellar medium contains, on average, only one hydrogen atom per square centimeter.
To achieve 1g acceleration in this medium requires the collector to have a base area of approximately 10,000 square kilometers. And even worse, Robert Zubrin and Tina Andrews showed mathematically that the drag force resulting from collecting hydrogen at high speed exceeds the thrust produced by exhausting it. Instead of accelerating forever, the ramjet could function as a brake, and the faster it wants to go, the more it could slow down. An analysis conducted in 2021 thus confirmed that the concept could physically be applicable in principle, but would require the engineering capacity of a civilization millions of years more advanced than us. Robert Bussard died in 2007, still believing the concept could be saved with the right modifications. 65 years after he published that letter, we haven't answered it. We have only been able to prove how cruelly difficult right is.
Number 6. Laser Sail, April 12, 2016. The 55th anniversary of Yuri Gagarin's journey into space, Russian billionaire Yuri Milner took a stage alongside Stephen Hawking in New York and announced that humanity would send a probe to another star within a generation. However, the probe would weigh only a few grams. The engine pushing it would be a laser far beyond any laser ever built. The project was named Breakthrough Starshot and can be called the most serious attempt in human history to cross interstellar space. The physics of laser propulsion was understood shortly after the invention of the laser. Light carries momentum. When reflected from a surface, it pushes that surface. With enough density and a light enough object, you can produce extraordinary accelerations. Physicist Robert Forward researched laser-driven sail concepts until the early 1960s. The Starshot plan envisions a probe on the scale of about 1,000 grams, attached to a sail about 4 meters wide each, but only a few hundred atoms thick. A ground-based laser array covering 1 square kilometer and capable of producing a total output of up to 100 gigawatts will illuminate each probe for about 10 minutes and accelerate it to 20% of the speed of light. At that speed, the journey to Alpha Centauri would take 20 to 25 years. The first data would return to Earth about 4 years after arrival. Researchers at Caltech published the first experimental measurements of laser-induced sail movement in a laboratory setting in early 2024. Thus, a small but real step was taken toward a functioning system. The engineering challenges are immense. There is still no solution for maintaining beam coherence over 4.24 light-years. Surviving interstellar dust at those speeds is a serious problem. Every dust particle is like a microscopic bullet. And they have no deceleration mechanisms. Every probe reaching Alpha Centauri would pass through there in hours and continue into the void. Even if these small spacecraft actually fly, the laser sail remains the first interstellar propulsion concept in history with a real budget, real engineers, and a real timeline. And, with its disturbing reminder, even our most daring plan can only wave from a distance as it passes the destination.
Number 5. Fusion rocket. Every star in the observable universe is powered by nuclear fusion. The process of forcing hydrogen nuclei together to form helium releases a massive amount of energy that dwarfs all other natural reactions we know. Our sun converts 600 million tons of hydrogen into helium every second, and has been doing so for 4.5 billion years. Since physicists understood this process, they have been asking this question: what happens if we put this inside a rocket? A dedicated fusion rocket, not the pulse detonation approach of Project Daedalus, but a continuous and controlled fusion propulsion system, is widely considered the most feasible way to reach truly interstellar speeds using physics as we know it. The attraction lies in the numbers. Fusion propulsion could theoretically achieve specific impulse values exceeding 1 million, about 2,000 times more efficient than chemical rockets. Exhaust velocities modeled in serious engineering studies reach 10,000 kilometers per second or more, fast enough to place Alpha Centauri within a 20 to 40-year journey at 10 to 20% of the speed of light. The problem is that controlled fusion continues to be extremely difficult. The ITER reactor under construction in Cadarache, France, represents the combined investment of 35 countries and decades of accumulated research. It has not yet produced net energy, however. Commercial fusion has been described since the 1970s as 10 to 30 years away, with a horizon that remains stubbornly fixed. The Princeton Plasma Physics Laboratory's PFRC-2 experiment investigated compact fusion reactor geometries small enough to fit inside a spacecraft. But no fusion engine has ever flown yet. What makes fusion propulsion so disturbing in its promises is its proximity. Unlike space-time warps or wormholes, fusion does not require finding new physics. Every theoretical obstacle is an engineering obstacle, a matter of material, containment, funding, and time. The universe shows that this process has been working for 13 billion years. At every sunrise, it shows us the engine we have not yet built.
Number 4. Antimatter propulsion, 1932. At Caltech, 27-year-old physicist Carl David Anderson, while examining the tracks left by cosmic ray particles in a cloud chamber, noticed something that was definitively wrong. One of the tracks was curving in the wrong direction in the magnetic field. The particle's mass was equal to the electron's mass, but its electric charge was exactly the opposite. Anderson had stumbled upon antimatter, and when he saw what happened when it was touched, his mind was blown. He realized that physics itself had handed him the most powerful and dangerous fuel. The energy released when matter and antimatter annihilate each other is not a reaction like burning hydrogen or splitting uranium. This is a 100% total energy conversion. The entire combined mass is directly converted into energy. The energy density of matter-antimatter annihilation is approximately 90 quadrillion joules per kilogram. This figure means about 10 billion times more energy than the liquid hydrogen and oxygen fuel that powers a spaceship's main engines, and about 300 times more than nuclear fusion. A theoretical beam core antimatter rocket, in principle, can reach speeds close to 40% of the speed of light. Alpha Centauri settles into about 10 years. The real problem is in production. CERN operates the most powerful particle accelerator ever built. The total amount of antimatter estimated throughout history is a few billionths of a gram, enough to power a 60-watt light bulb for just a few hours. The energy cost of producing 1 gram of antihydrogen with current methods reaches tens of trillions of dollars. And yet, the universe produces antimatter every moment, every second. Cosmic ray collisions are still producing it in the upper atmosphere right now, just as they have for billions of years. Antimatter is the most powerful fuel the laws of physics will allow. We have been trying to collect it for less than a century and have only been able to obtain enough to cast a shadow.
Number 3. Generation ship. To reach another star, there is a method that doesn't require new physics or unproven technology. You build a ship large enough to carry a great civilization. You point it at a distant sun, and you accept with clear and emotionless honesty that those who arrive at the destination will not be those who set out. It will be their descendants. They will be individuals born in transit who have never seen Earth. The generation ship concept has been seriously examined since at least the British Interplanetary Society's 1984 World Ship Analysis. The physics is simple. At 1% of the speed of light, Alpha Centauri is about 420 years away. As much time has passed since the Mayflower crossed the Atlantic. If we drop this speed to 1,000th of the speed of light, the journey extends to 4,000 years. Biologists have estimated that for long-term genetic health, the minimum viable breeding population on such a journey should be in the thousands. Some analyzations suggest 10,000 or more people. The alternative within this category is suspended animation. Between 2013 and 2016, NASA funded research into human torpor, suppressing metabolism to about 10% of its stable function. Results suggest 2 weeks are possible with near-term technology. Decades remain speculative. The generation ship asks for a civilizational solution, not an engineering one. Will a society be able to maintain its purpose for centuries? We built cathedrals that took 300 years to complete. We trusted that generations yet unborn would finish what the founders started. The generation ship is a similar act of faith toward a star.
Number 2.
Alcubierre Drive, 1994. Mexican theoretical physicist Miguel Alcubierre was left alone with a problem most of his colleagues didn't even find worth taking seriously. He wanted to know if the drive from his favorite sci-fi universe could be mathematically possible. He ran the equations of Einstein's general theory of relativity. What he found was that the universe apparently had a loophole, and he published this in a paper titled The Warp Drive: Hyperfast Travel Within General Relativity. Alcubierre's mechanism does not make a spacecraft faster than light. Instead, it does something stranger. It warps space-time in front of the ship and expands it behind, creating a bubble of locally flat space-time in which the craft can move freely. The ship never locally moves faster than light, but the warped space-time bubble around it can travel at many times the speed of light without violating special relativity. The passenger inside feels no acceleration forces. The journey to Alpha Centauri could take days, hours, or minutes. Then came an obstacle. To create the Alcubierre geometry, the equations require a material with negative energy density, what physicists call exotic matter. Such a material has never been observed in nature. Early calculations suggested the energy required would exceed the total mass energy of the entire observable universe. Later refinements lowered the requirement significantly to the mass energy equivalent of Jupiter, but these were still just thoughts. In 2023, researchers published a paper showing that a subluminal warp drive using only ordinary positive energy could theoretically be built. Faster-than-light travel is not achieved, but it is possible to move a passenger in space without G-forces. And now we have come to the truly scary and interesting part. Listen carefully.
Number 1. Wormholes, 1935. Albert Einstein and Nathan Rosen described something their equations implied, but neither of them fully believed in: a bridge between two separate points of spacetime, a kind of tunnel passing through the fabric of the universe that could connect two galaxies as simply as two rooms. They called it the Einstein-Rosen bridge. Then in 1985, Carl Sagan was writing a novel and needed his protagonist to travel between stars without going outside of physics. He called physicist Kip Thorne and asked if a traversable wormhole was theoretically real. Thorne took the question seriously and published a formal analysis in 1988. The results were mind-blowing. A traversable wormhole that a human could pass through and survive was not forbidden by general relativity. It would require exotic matter to keep the throat open against gravitational collapse, but the structure was geometrically consistent with the laws of physics as we understand them. A traversable wormhole doesn't reduce our distance to Alpha Centauri, it eliminates it. You enter from one side and exit 4.24 light-years away instantly. Stars that require thousands of years in chemical rockets will become as accessible as the next city. Isn't it an incredible event? In 2013, physicists Juan Maldacena and Leonard Susskind proposed something even more disturbing. ER equals EPR. This suggests that quantum entanglement could be physically identical to a microscopic wormhole. Every entangled particle pair in the universe might be connected by a thread in the fabric of spacetime. Interstellar distance is not a physical barrier, it's a definition of how spacetime is currently arranged. The wormhole suggests that distance has always been a thought, a wrinkle in the universe's own math that we just haven't found yet. If you want to see more videos like this, like the video now and don't forget to subscribe.